And I just want to warn you, we were given the option to work at home today due to the weather. And for some reason, when I try to teach on my MacBook with a tablet and write on the tablet, the Smart Notebook doesn't really interact with the MacBook and my tablet very well. So I'm going to do my best. I think if I don't change my ink color at all, I will be okay. First hour I was okay, and then second hour did not go well because I was trying to change my ink color and stuff. So bear with me. Hopefully it'll be okay. All right, so today we're going to go through two sections because they're both pretty short in a short amount of time. So we will get started. What the first thing that we are going to do today is talk about, is something a linear function or not? And basically a linear function is a straight line, okay? So if you have a linear function, these are the rules that make something a linear function or not, okay? So the first thing is, if you have a linear function, you could never have something like this, where x and y are multiplied together, okay? That would not be a function. You also cannot have x or y in the denominator. So you couldn't have like 4 over x equals y, okay? Or x plus 4 divided by y equals 5. X and y cannot be in the denominator. And then another thing is, they can't be exponents, okay? So you couldn't have like 4 to the x plus y equals 10. That, if you graphed it, would not be a straight line. Or if you had something like 2 to the y equals x, okay? Y cannot be an exponent. X and y also can only have an exponent of 1. So you couldn't have like x squared equals y, or x equals y to the third minus 2, okay? Your exponents of your variables can only be 1. And then the last thing, you cannot have a variable under a square root. So you couldn't have like the square root of x equals y, or x plus the square root of y minus 2 equals 7. You can't have a variable under a square root, okay? So if I look at this chart here, kind of in the middle of my page, it says, what is a function, what isn't? These over here are all functions, okay? So x is just by itself, that's good. It's to the power of 1. It's not under a square root. It's not a denominator of a fraction, so that's good. Same with the second one. The third one, our x and our y are to the power of 1, not under a square root, not as an exponent. Those are all good linear equations, and if you graphed them, they'd be a straight line. These over here are, however, are not linear functions. They would not be a straight line, okay? The first one is because you cannot have a variable on the bottom. That is why it is not a linear function. The second one is because we cannot have a y squared. And the third one is because we can't have x times y, okay? So today, one of the things they're going to ask you is, are things a linear function? And if they are, you don't have to say anything but yes, but if it's a no, you have to give a reason why, which is like what I did here, okay? Now here is where it's probably going to be a pain here. Oh, that wasn't too bad. Okay, good. So that's another thing. Either the top of my page gets cut off or the bottom of my page gets cut off. So it's just kind of a pain. All right, so when we look at this, It's basically asking us, if we graph this, would it be a linear function? And what you could do is split this up into two fractions. This would be like 1/5 x plus 12 over 5. This would be a linear function. So you just have to say yes. The x is on the top of the fraction. It's to the power of 1, so that is good. This second one here, notice we have an x in the denominator of a fraction. So that is not going to be a linear function, and it is because you have an x in the denominator. Okay. The third one is not going to be, and that is because we have x squared. The fourth one is not going to be, and that is because we have y squared. The fifth one, notice my x and my y are both to the power of 1. They're also both on the top of a fraction. They're not anything in the denominator, nothing under a square root. So that one's good. And when it is a function, you just have to say yes. For 6, this one is not going to be a function because you cannot have x in the denominator. Okay.
Question. So
yeah.
whenever it's not a function, we give the reasoning.
Yes, but if it is a function, then you just have to say yes.
Right.
Good question. All right, x times y, you can't have in number 7. So we're just going to say no because we have x plus or times y. In number 8, it's also no because we have x in the denominator. On number 9, we have the square root of a variable, and you can't have that. And then number 10 is also no, because we can't have the square root of 9 plus x. You cannot have an x under a square root. Okay. So now we're going to go to this page, and this is asking us if we have a linear relation or function again. And what this says is that we have Melina and Helena work part-time at a smoothie store. The number of hours they worked increased for the first 5 weeks on the job. The graph over here on the right models Melina's weekly earnings, and the table below models Helena's weekly earnings for 5 weeks. State whether each is a linear function and explain. So this first one is easy for Melina over on the right. Notice that you can connect those points in a straight line. So that would be a linear function. Okay, because you can connect those dots and make a straight line. Down here for Helena, to be able to tell if this is linear or not, what you can do is see how much is this going up from $60 to $120 in 1 week. And here she increased $60. From 120 to 180 is another $60. From 180 to 210 is an increase of $30. And from 210 to 240 is an increase of $30. Because these are not all the same increase, this would be no, because it's not. And as long as you have that drawn there, like the plus 60, plus 60, plus 30, plus 30, then I know that it's not, because it's not the same amount of increase each week. Okay. This one here says Shayla and her brother Malcolm both left home on their bikes at the same time. The graph shows a function modeling Malcolm's distance from home over time. State whether the function is a linear function. So let's start with the graph again. So if something were a graph, or were a linear function, it would have to be just one straight line. This, she's going away from home and then she starts going back to home. It's not just one straight line. So this is no. Okay, not a linear function. Over here, you would look at how much is Malcolm going away from home every 10 minutes. And in the first one, he went 1.5 miles. From 1.5 to 3 is another 1.5. From 3 to 4.5 is another 1.5. And from 4.5 to 6 is another 1.5. So there we're going the same amount each time. So that one is linear. And if you plotted those points on a graph, you would get a straight line. Whereas up here, if we plotted these points on a graph, we would not get a straight line. Okay. All right. So let's go to this. Here is a line symmetry, and we're going to be talking about how do you tell if something has line symmetry, okay? So some graphs of lines or curved lines are going to have line symmetry, some do not. A line of symmetry would be a line that would cut, like if you folded this first line here, this parabola, if you folded it over the line I just drew, the left side and the right side would coincide. That is a line of symmetry. And when you name a line of symmetry, what you do is you actually name it as the vertical line. And that vertical line is x equals, and notice x would equal 1 here, 2 here, so it would be x equals 3. So this one does have line of symmetry, and our line of symmetry is x equals 3. This next one here, if I drew this line here, and you got to think about this continuing over here, this one also would have line of symmetry, and your line of symmetry would be that vertical line again, which is again x equals 3. If I look at this one, if I drew this vertical line, that would, and I folded the left and right sides, the left and right sides would match up. And so this one does have line symmetry. And this line here is actually the y-axis, or you could name it as x equals 0. Either of those is fine. Okay. Now this last one, a diagonal line like that does not have line symmetry. You could not draw a vertical line or a horizontal line that would allow you to fold that in half and the left side would map on to the right side. So a diagonal line like that is never going to have line symmetry. Okay. The second thing we're going to talk about here is point symmetry. Point symmetry is a little bit harder to see, but if we look at this first example here, a point, if something has point symmetry, it would have a point where in this case it's the origin, where if you took this graph and you rotated your graph 180 degrees, so that would be like taking your graph and turning it upside down. You'd be thinking, if I did that, if I turned this graph 180 degrees, would this part map on to this part? And it would. Okay, so that means it does have point of symmetry. And if you ever want to label that as point of symmetry, POS, that's okay. And then you have to list what is the point of symmetry. What point would you be rotating around? And in this case, it's the origin, so 0, 0. Now, if that's hard for you to see, like, would it map onto itself if I turned it upside down? Another thing you could do is think about like this point and this point. If you reflected that point about the point of symmetry, would this point reflect onto here? If you drew from here to that point of symmetry and then the same amount in the opposite direction, would this point reflect onto here? And it would. If you picked maybe like this point and this point, and you reflected it, this would be easier if I had different colors. If you reflected it, would this point reflect onto here over this point? And it would. Okay, so this one does have point of symmetry. Now here, if I thought of this as my point of symmetry and I turned this page 180 degrees upside down, would that V-shaped line go onto itself? And the answer is no. It would actually look like this if you did this. Okay, you would get an upside down V. So this has no point of symmetry. Okay, this just shows kind of rotating this one and it has point of symmetry. This just shows what it would look like if you did turn it upside down and it does not have point of symmetry. Okay. Then example 4 is asking us, does this have line symmetry, point symmetry, or neither? Okay. So if you look at one here, this has line symmetry. And so we would just say line. Okay. And then you have to name this line. And remember, we do that with x equals, and x equals a -2 there. If I looked at this second one, there's no way that I could draw a line that would cut it in half so that I could map the left and right sides. And there's no point that I could rotate out about to get that figure to map up onto itself. So this is asking us, does it have line symmetry, point symmetry, or neither? This has neither. Okay. Now if I go to this one, I have point symmetry. Okay. And so this one, if I turned it upside down, this section would map on to this section. And so it has point symmetry. And I have to give that point that it would rotate about. And that is the point 0, -2. And again, like I said, you could choose this point up here and this point down here and kind of think, if you reflected it over that point, would you end up with this point down here? You could pick this point and this point and look, if you reflected this over that point, you would end up here. From here, you'd end up there. Okay. Now this last one, there's not a vertical or horizontal line that I could draw that would cut it in half and allow that to map onto each other. There's also, if I turned it upside down, it would just kind of, you know, go off. I mean, I'm not drawing this really exact, but it would look something like this. So there's no point of symmetry. There's no line of symmetry. So this we would just write neither. Okay.
I have a question.
Yeah.
So for the first one, the line x -2,
Yeah.
would there be another one for x, or would that be the only one?
That would be the only one.
Okay,
So
thanks.
Yep. It's like, what line could you draw and fold that in half so the left and right side would map onto each other? If we look
why
down,
isn't the third one both?
say that again.
Why isn't the third graph both?
Why isn't the third one both? Okay. Because like a line of symmetry here, this would map over to here, and this would map over to here. If I drew a line this way, okay, then this one would line down here, this one would go up here. So if I drew a vertical or horizontal line there, I could not get the original to map onto itself. Does that help? like the only way that would have line symmetry is if it were a parabola on the top and a parabola on the bottom. That's the only way you could draw a line where the left and right would map onto each other. Or if I did a vertical line or a horizontal line, the top and bottom would map onto each other. Okay. So now down here, this one you kind of want to think of extending this line down here. This actually would have point symmetry. Okay. And the point symmetry for this would be at this point, which is -2, -2. All right. This one here, this diagonal line, we talked already today about the fact that diagonal lines do not have lines of symmetry. Okay, you couldn't draw a vertical or horizontal line that would cut it in half. However, what you could do is pick any point on this line and turn your line upside down, or turn the graph upside down, and that line would look exactly the same. Okay, so it turns out that this has point symmetry, and because a line extends indefinitely, there's no actual point of symmetry. Every point on the line is point of symmetry for this one. Okay, so it's when it's a diagonal line, all points on the line are points of symmetry. Okay. Then if I look at this last one here, I could draw a vertical line here. You got to think this would keep going. That would be line symmetry, and that line is vertical, so it's x equals, and it's x equals 1. Questions? Okay. So the next thing we're going to talk about is, so we're actually going through 2 sections today, and the second section we're going to talk about is talks about end behavior. And you guys have seen this before earlier this class, where this means as x approaches positive infinity, and this one here means as x approaches negative infinity. Okay. And when they give you a graph and they ask you to write the end behavior, this is what they're saying. As you go towards the left on a graph, your x is approaching negative infinity. So think about if you start at 0 and you keep going along this line, your x is going to keep getting smaller and smaller and smaller. So your x is approaching negative infinity. Then what you do is you look at your graph as you go from x equals 0 and keep going. You have to say, what does your graph do? And when you talk about your graph, you say f of x. And your f of x here keeps getting smaller and smaller and smaller. So that is going to also approach negative infinity. Okay. Then if we think about starting at the origin and going towards the right, our x is going to approach positive infinity. So as I travel along this line, my x is getting bigger and bigger and bigger, and it's approaching positive infinity. And then it's going to ask us what happens to our f of x. And notice our f of x keeps getting bigger and bigger and bigger. So I'm going to say my f of x approaches positive infinity. Okay. Now, if I go to this second one, notice here, as you travel from the origin towards the left, your x is going to approach negative infinity. And they want to know what happens to your f of x then. So as you're going from x equals 0 and keep going towards the left, Notice this line keeps getting smaller and smaller and smaller again. So your f of x is approaching negative infinity. Then if I go this way, okay, as x approaches positive infinity, my f of x, which is my graph, keeps getting bigger and bigger and bigger. So that is approaching positive infinity. Okay. Now we're going to skip down here because you're going to have problems like this today. So you're going to ask yourself, as you go to the left, as your x approaches negative infinity, what is your f of x doing? And that is getting smaller and smaller and smaller, so that approaches negative infinity. Then you're going to ask yourself what happens as your x approaches positive infinity, and then notice that your f of x approaches negative infinity also because it keeps getting smaller and smaller and smaller. Okay. This one here, as x approaches negative infinity, as we go to the left, notice here your graph is getting bigger and bigger and bigger. So our f of x approaches positive infinity. And then as we go to the right, as our x approaches positive infinity, our f of x, notice, is getting smaller and smaller and smaller. So our f of x is approaching negative infinity. And then the last thing we have to think about is what happens if you have a horizontal. Yeah.
On the first one, it's going both directions, but for both of them, you have them negative.
Yes. And that is because notice both of these are going down. They're both going in the same direction.
Oh,
so they're
okay.
Yep. Whereas this one, notice, this is getting bigger, so it's going to positive infinity. This one's going down, so it's going to negative infinity. Okay? All right. So this one here is a horizontal line, and as you go towards the left, your x is approaching negative infinity. But notice this, your graph never changes, okay? This is the line y equals, this would be -1, -2, -3. So this is y equals -3 all the way across. So as your x gets smaller and smaller, your f of x is going to always be equal to -3, not 3. So let me just take that off. Your f of x is going to approach -3. And then as you go to the right, your x approaches positive infinity again, and your f of x is going to equal, I shouldn't have said approach here, I should have said equal, because it's not approaching it, it's equaling -3. Okay, so that is how you would do a horizontal line.
I have a question.
Yep.
What's the difference between x and f and x?
Good question. Your x is referring to your x variable, the x-axis. F of x, always think of f of x is really your y. The difference is if it says f of x, that means it's a function. So f of x is a function notation for y. So when they're saying f of x here, they're talking about your y.
Okay.
Okay. All right. So when we look at this, the next thing that we're going to talk about is relative maximums and relative minimums. So you're going to have graphs throughout the course that are not just linear. They are going to go up, then down, then up, and maybe down and up and down and up and down. And what's going to happen is you're going to have points where the line turns, and those are called turning points. So I have a turning point up here, and I have a turning point down here. Those turning points are going to be called minimums and maximums. And up here, this is what we call a relative maximum. And this one down here is called a relative minimum. Now, you would think when they ask you today, where is your relative maximum, you would read it over to the y to see how high that line goes. But instead, what they want is they want to know at what x value is your relative maximum and at what x value is your relative minimum. So this one, if you kind of follow it down, is going to be a relative maximum at x equals a -4. And then the relative minimum is going to be at x equals, at x equals. Now notice here, that's right on the y-axis, so x would equal 0. Now, most of the time, most books, I should say, would set the problems up like this, where a relative max and a relative min are always on an actual x coordinate. But unfortunately, your book doesn't always do that, okay? So if I look down here, notice this relative minimum is not, if I follow that down to the x, it's not right at an x coordinate. So what you would say here is that it's between, you don't even estimate it, you just say it's between x equals 0, which is right here, and x equals -1. Okay? Sometimes when you follow it down like this one, I'm not going to be able to do a very good straight line here, but this one is pretty close, okay, to x equals 1. So what they do there is they'll say you have a relative max near x equals 1. Now, when I put them on a test or a quiz, I'm going to put examples that it would be right at an x coordinate. So it would be right at x equals 1 or right at x equals -1. But unfortunately, our book doesn't do that. So what I would say is if it's ever halfway between or kind of halfway between, then I would say between x equals 0 and x equals -1. If it's close to one of them, then you do the near x equals 1 or x equals 2, whatever it may be. Okay, so we will go over some examples like this. So if I look at this, again, if you look at the minimum here, this would be a relative minimum. Okay, and notice again, it's not right at an x value. So this is x equals -1. This is x equals -2. So you could say this one is near x equals -1, or I'd also accept that one's not, I mean, it's closer to x equals -1 than x equals -2, but you could also say it's between x equals -1. Oh, and I'm writing this in the wrong spot. Sorry, I'm writing it as a maximum instead of a minimum. So I just put this in the wrong spot, sorry. So you could say it's near x equals -1, or you could say it's between x equals -1 and x equals -2. Either of those would be acceptable to me, okay? And then for our max, that's right here, okay? And that does look like it's right at x equals 0. So I put near here. Actually, you should say you have a relative max at x equals 0, okay? So you would say where your relative max is and where your relative min is. Now this one, if you look at it, it keeps getting bigger and bigger and bigger. So our maximum is going to be infinity. And then it does come down and kind of flatten for just a little bit and then goes down, but it doesn't dip and go back up. It doesn't go up and come back down. It just kind of flattens a little bit and then goes to negative infinity. So when it doesn't have a point that dips down or goes up and comes back down, this one has no relative maximum and no relative minimum, because your relative max is really infinity, which we wouldn't write that, and your relative min is negative infinity. Okay. So last question here, it's saying that we have a table of values and then they also have a graph of it. Okay. But I want to explain something with this table. First of all, when they have this table, notice they have the numbers going up by 1 each time. Okay. So they go -2, -1, 0, 1, 2, 3. If your values are increasing and they're not just haphazardly put there, you can kind of tell where your zeros are going to be in a graph by looking at the signs of these two values. If these are both positive, then you can pretty much figure that these 2 points are going to both be above the x-axis because they're both positive, and you're not going to have a 0 in between those two. In between 2 and 3, they're both positive, so we're not going to have a 0 in between there. But then if you look from 0, that's +3, and 1 is -2. When you have 2 consecutive points where 1 is positive and 1 is negative, what that means when you graph those, like 0, 3 is here, 1, -2 is down here. When you graph those, you're going to cross that x-axis, and an x-intercept, when your graph crosses your x-axis, that is a 0. And just so you guys understand, where your graph crosses the x-axis would be an answer if you were solving an equation. Okay, so if I gave you something like y equals x to the third plus x squared minus x equals 7, and I said solve this equation, if you could look at a graph of it, where it crosses your x-axis are called the zeros or x-intercepts of that graph. Okay, and if you ever had a table of values like this, if you find a situation like down here from -1 to 42, one's negative and one's positive, so if you connected those 2 points, it has to pass through the x-axis to do that, and there's going to be a 0 somewhere between 2 and 3. So the first thing they ask us here is, where are our zeros? And again, I'd rather these be at actual x values, but our book doesn't. So what it says for this one, I would probably say that is near x equals 1. If somebody else said it's between x equals 0 and x equals 1, that would be fine. Okay. Our other 0 is right here. Okay, now that one I would say is at x equals 2. So I have one that's near x equals 1, and I have one that's at x equals 2. Then they want us to say, where is this first relative minimum? Okay. Now, again, that's not right at an x value, but it's close to x equals -1. So I would say this is near x equals -1. Then I have this relative maximum up here. So this was a relative min down here. This is a relative max up here. Okay, so that relative max is again not right at an x value, but I would say it's probably near x equals 0. And if somebody else said it was between x equals 0 and x equals a -1, that would be absolutely fine. Okay. Then they're asking us for the second minimum. Okay. This one probably is almost halfway in between. So for that one, I wouldn't say it's near x equals 1 or x equals 2. I would say it's between x equals 1 and x equals 2. So that's this relative min right here. It's between x equals 1 and x equals 2. Okay. Now, if I go down to our last question here, again, you could see that there's going to be this is going to be a 0 right here because your y value is 0. Okay. And if you look here, -1, 0 is a 0. So you have a 0 at x equals 0. Then notice these 2 points. One is negative and one is positive. So in between 0 and 1, which is right here, there is going to be a 0. And I would say that's about halfway between. So we're going to say between x equals 0, which is this point right here, and x equals 1, which is this point right there. Okay. And then notice we have another 0 over here. And for that one, again, it's closer to x equals, what is that? X equals 3. But you could, so somebody might say near x equals 3, or I would probably on this one say between x equals 3 and x equals 4. Okay. Then they're asking us, where is the relative min? Well, your relative min is down here. And I would say that's near x equals 0. If you said between x equals 0 and x equals -1, that would be okay. And then your relative max is up here. And for that one, you could say near x equals 2. That's what I would probably say for that one. But if you said between x equals 2 and x equals 3, that would be okay. All right, it looks like I went the entire time. I'm sorry about that. Your assignment then, guys, is right here. And there's 2 page numbers because of the fact that we have 2 sections. Okay, so that is your assignment. And I made it due, it's in Schoology, so you'll see it there. I made that assignment due on Monday night. Monday we don't have school, so it's due on Monday night at midnight. And if anyone is going to join me on Monday night at 7, you should see that in your calendar if you go to the left side and find the calendar on Teams. You might have to hit the 3 dots to access that. And I'll be setting up a meeting for Monday night and Wednesday night at 7 p.m. for the 2 sessions. If you did not sign up for the sessions and the test, you have to do that. So make sure you go. Your parent got an email and they would have to go in, and there's a link to sign up for the test and the sessions. Okay. If you do not have a calendar meeting, send me a message on chat and then I will invite you to the meeting. Okay. Have a great weekend. Yes.
We're already supposed to have a meeting, or you're going to schedule it?
There's not a meeting there yet.
Okay.
I get the names later today and then I'll be setting it up.
Okay.
Okay. Anyone else have questions? All right, you guys are free to go once you copy that down. And this is due Monday night at midnight. Have a great day, guys. Goodbye. Zach, are you okay with everything then?